Okay, hello everyone. I have shared my screen and I hope everyone can see the slides and can hear me clearly. If not, please let me know. Okay, so before starting uh, today's lecture slides, they are going to be relatively short as compared to our previous lectures. So once we are done with the slides and if we still have some time left, so we can use that time to answer any questions you have related to previous lectures. Okay. So, or if you want to discuss anything related to the course or to the labs, we can use that time at the end of the lecture. Okay. Okay. So, uh, last time we talked about branch instructions and arithmetic instructions, and in this set of slides are for today. We are basically going to talk about the AVR microcontroller itself and focusing on the features of the AVR microcontroller and the Arduino board. Personally, I feel that this set of slides should have been the first lecture, should have been discussed in the first week. Uh, but I can do that next time when I'm offering the same course. So I can count it as an improvement. So because I think the right place for this set of slide is at the start of the course, not like after 4 or 5 weeks. Okay, so the topics we are going to cover are what is the difference between a microcontroller and a microprocessor. Then we have a look at most common microcontrollers, like very brief and very high level. Our look at I have a very brief look at most common microcontrollers, and then we will go through the features of AVR microcontroller and what different AVR microcontrollers are available within the AVR family, and then we will have some slides on the Arduino board itself. Okay. So, general purpose microprocessor, the feature about the most when you want to compare the microprocessors with the microcontrollers, the most important our outstanding feature is the general purpose microprocessors. They are a chip in their own, and all other uh, components of a computer system, like for example RAM, read-only memory, or data memory, or RAM, or timer, or serial communication port, or other I/O ports, they are not residing, or they are not built on the same chip as the microprocessor. So all these components are external to the microprocessor, and then they are connected with the microprocessor through data bus, address bus, and control bus, which basically mean that each of these components are a chip on their own. And these buses, data bus, address bus, and control bus, whenever communication happen, the communication crosses the chip boundary. Okay. Uh, so these general purpose microprocessors, they are built for general purpose computing. They are not optimized for performing a specific functionality, and they have all the features which are required to run any general purpose application. For example, on your laptop or on desktops or even on your phones, you can run different applications. Like for example, you want to run word processor, you can also run some game, or you can open web browser, you can run different kind of scientific tools, whatever you want to run. Most of the applications you can simply run on your desktop or laptops. Why? Because how it becomes possible, because the underlying hardware features of the microprocessor, uh, this support uh, uh, this support all different kind of applications. So for example, in this, okay, I will take this question or comment. Let me first complete this part of the slide. So, for example, in when the computers which are built using general purpose microprocessor, they have uh, external memory, both read ROM or RAM, both are external to the microprocessor, and the size of the physical memory is modifiable. Like it depends upon your application or your requirement, how much memory you want to, what is the size of the memory which you are going to interface with your microprocessor. As long as as the size of the memory is within the addressable range, you can select any size. Okay. Uh, Also, typically the memory is large enough to support operating systems because operating systems are is a large piece of software, and then if memory is large and you can run the operating system, then then your systems can offer all different services which are part of the operating system. For example, in this system, you can run multiple simultaneous processes or applications. For example, you can run a word processor and a web browser at the same time, right? Okay, let me have a look at the stats. Hi, Professor. The lab 3 deadline is due time, but my lab class is usually on Thursday. Do I have to show up to the lab today to show my work to TAs? Okay, please remind me of this at the end of the lecture, okay? So then I will like take care of this. Uh, okay, Andrew, you hear me right? Okay, thank you. Okay. Uh, okay, but when the problem with general purpose microprocessors are actually the systems which are built around general purpose microprocessor. The problem with them is that they become more expensive. Why? Because one thing is like you have a processor which has much more features as compared to a microcontroller, so it can perform a lot of other things as compared to the microcontroller. Also, you need to buy separate chips like for RAM or ROM, or separate chips for which actually provides you the functionality of timer or serial communication or IO port, and then interface with general purpose microprocessors. So it becomes more expensive, and not only that, the size of the system, it also increases. And these systems which are built around general purpose microprocessor, normally they consume much more power as compared to the designs built around microcontrollers. So that's why that they are not a good fit for embedded systems, because embedded systems are limited on power budget. Uh, Also, the communication happening between your general purpose microprocessor and all the other components components in your system, that communication incurs high latency because signals are traveling between chips, not within a chip. Okay. Okay. So when we look at microcontrollers, on the other hand, the difference is that your CPU and the other components in your system, like your memories, are your peripherals or timers, they are all of them are on a single chip. So your whole system is embedded, our whole system is built on a single chip. Uh, so these when you develop a system around microcontrollers, so that system is most of the time meant to perform a specific task. For example, let's say you just want to read some values from sensors, and then based on those values you want to perform some task. For example, you want to turn on cooling system in your home. So then if this is the kind of system, or this is the kind of the application you are thinking to develop, then microcontroller is a much better fit as compared to the microprocessor, because uh, it has all the features, or it fulfills all the necessary requirement which are needed for your application, and it doesn't provide anything extra. Uh, so microcontrollers, they are cheaper as compared to the microprocessor, and again the reason is like you have everything on the single chip, so less transistors means you are paying less. But then all of them are limited in their capabilities as compared to the microprocessor, general purpose microprocessor. Microcontrollers, they are designed for low power consumption, and they are much smaller in size as compared to the systems built around microprocessors. The issue is that the size of the memory, since it is on chip, it cannot be changed, that it cannot be configured according to the requirement of a user For example, in the previous figure, we were interfacing the external memory, and we can select that what is the size of the memory which we want to interface. Also, memory is small typically, and the size is so much small that it cannot host an operating system, and hence it cannot execute an operating system. As a result, uh, typical designs or systems built around microcontroller, they don't allow for multiple applications or processes to run at the same time. Uh, so Microcontrollers, they come in different flavors. So for example, the most popular are 8-bit microcontrollers or 32-bit microcontrollers. So when we say 8-bit microcontroller, it basically means that all the internal registers of the microcontroller are 8-bit wide. And when we say microcontroller is a 32-bit microcontroller, it means that the internal registers of the microcontroller are 32-bit wide. So example of 8-bit microcontroller is AVR family of AVR. Most of the microcontroller within the family of the AVR. For example, the one which we are covering in this course at Mega 328P. It is a 8-bit microcontroller. And then there are some other like PIC, HCS12, and 8051. So 8051 is from Intel, and PIC is, I guess it is from Microchip or PowerPC. I'm not sure, but it is another 8-bit microcontroller. And these microcontrollers, just a side note, they are not compatible with each other. So for example, which means if you have a written up program for AVR microcontroller and you want to run the same program and on 8051, it will not be possible. Why? Because maybe they differ in number of the registers, they differ in the instruction set, what kind of instructions are supported on 8051, also on the syntax of those instructions. For example, in AVR, you have instruction, let's say, branch equal. So maybe in 8051, they have an instruction which does exactly the same thing, but the name of the instruction is different. For example, it says branch if zero instead of saying branch if equal. Okay. So then that's why if you write a program for like one microcontroller, you cannot simply port it to a different microcontroller. You will have to like most probably modify it, rewrite it, and then compile or assemble it again to generate the binary code or the machine code, because machine code depends upon the hardware and it is different from one microcontroller to the other. On the other hand, we also have 32-bit microcontrollers. For example, our microcontroller are the version of PIC, which is 32-bit wide, and an AVR microcontroller, which is also 32-bit wide. And there is only one 32-bit microcontroller in the AVR family. All other are 8-bit wide. So if we have like different families or different kind of microcontrollers available, and let's say uh, build up we want to build a product or an application around a microcontroller. So how we will select a microcontroller of our choice, like based on what criteria we will make a choice for selecting the microcontroller. So for that, you can have different, you need to look for different parameters. And one of them is computing need of the task, which basically mean the project which you are like, let's say, as I gave you an example earlier, let's say you want to build a project which simply reads the sensor values, and then based on that values either turn on the cooling system or the heating system in home, right? So for this task, you need to analyze that among available microcontrollers, which one offer you the required speed, like which can actually execute your program to complete the task at acceptable latency. The other thing is packaging. So there are some, it is, if you look at microcontroller, for example, even at 328, microcontroller 328P, it comes in different packaging. So some of them, they are more compatible if you are prototyping your product, or you are just like a new person, a beginner to work with the microcontrollers. as compared to other packaging which are actually meant for mass production. Once you have prototype your project, then you can use the different packaging. So that is also a factor which you need to consider while you are selecting the microcontroller. So basically, it's mean if you are prototyping, you will select one type of packaging, and if you are done with your initial testing of your product and you now want to produce it at the mass level, then you will have the same microcontroller but in a different packaging. Okay. Also, power consumption. We don't want to we don't want to build a product or to design a product which actually consumes too much power, because most of the time microcontrollers are used in systems which are battery backed. And they are limited on power. So we want to have a microcontroller which consume relatively lower power. Also, the other thing you need to look at is RAM or ROM capacity. So, for example, the functionality which you are going to implement, the code for that functionality, how long is it long or how big it is? Can you like host it or place it within the read-only memory or the code memory of the given microcontroller? If it is larger than the size of the code memory, then it's mean that given microcontroller is not suitable for your purpose, right? Similarly, the amount of data that which will be processed or which will be produced by your code, can you hold or place it in the RAM size of the given microcontroller? If yes, then you can select it. If not, then you need to look for another microcontroller which is good for your purpose. Again, another thing is, or another factor is that how many I/O pins and timers are available. For example, if you are designing a project which actually reads a lot of sensors and or it monitors the values which are read by a lot of sensors, and then based on them it takes different actions, then it's mean that you need to have maybe multiple outputs and multiple inputs. And then maybe you also will need multiple timers. So again, it all depends upon what kind of application or what kind of design you are developing. Ease of upgrade to high performance, low power consumption future versions of the same microcontroller. Let's say you have analyzed all these factors like speed, packaging, power consumption, RAM, ROM capacity, and number of I/O pins, and after that you have selected a microcontroller. The one thing which you also need to consider is that uh, will this microcontroller will it be easy for me to upgrade my product by using the future version of the same microcontroller? The future versions which offer high performance are like more speed and low power consumption, right? uh, so how easy for you to shift to the newer version of the same microcontroller? And another factor is like how much it will cost per unit. The other aspect for while you are trying to make a decision for selecting a microcontroller will be availability of hardware and software development tools. Actually, it is very crucial. So, for example, we are using AVR microcontroller 328P. Why? Because the Arduino IDE, it is like widely used. There is a strong and active user community, and it is open source, and the help is available. And the development tools, they are free. You don't need to pay anything for that, for example, for using Arduino IDE. And also, when we say availability of hardware, for example, in our case, you have the Arduino boards, which are there for you to quickly start prototyping your project without having to actually do wiring on the PCB board, a printed circuit board, and put all the elements or all the components along with your AVR microcontroller. So the board is already available there. So it's easy to start developing using those available hardware software tools. And the other thing is that you want to make sure that the microcontroller you have selected, it is widely available and available from reliable sources. So it is not like a small only. Let's say you select a microcontroller which is developed or which is manufactured only by a small company in some small company which doesn't have a lot of customers. So maybe in future it will stop manufacturing that microcontroller, and that's why it will not be a good idea to use it in your product, because if in future they stop manufacturing it, then you will not be able to build your product around that, and you will have to move to another microcontroller. So, AVR microcontroller, first thing, as I said earlier, all the microcontroller and AVR microcontroller family, they are 8-bit, except AVR32, and these AVR microcontrollers are divided into four families. We will have a slide on those families in a while. Uh, the problem with the problem with AVR microcontrollers is that they are not compatible across families, which basically mean that you cannot move your code which you have written for one microcontroller in a given family, and you cannot run the same code as it is on a microcontroller, AVR microcontroller in a different family. So you will need to modify and recompile on the target microcontroller of different family before you can run it. And again, this comes basically from the fact that yes, all of them have 32 registers, but then they differ in the available instruction set. So for example, in some micro AVR microcontrollers, there is no multiply operation or multiply instruction. So if you have written, let's say, a program on AVR let's say at mega 328p, and your program uses the multiply instruction, and then you move it to, let's say, another AVR microcontroller which doesn't support it, then you will not able to run your program, and you will have to rewrite it. Features, we have actually discussed this in a previous slide set, but AVR microcontrollers, all of them follow the RISC architecture, which basically mean that they have a reduced instruction set. Their instructions are not complex, uh, and they have the Harvard architecture, which basically mean they have separate address and data bus and control bus for your code memory and for your data memory. Uh, and all of them have on-chip RAM, ROM timers, and I/O ports. So this is like, we have seen this figure, I guess, in the first lecture, but this is how your AVR internal architecture of AVR microcontroller looks like. I mean, definitely there will be variations when you move from one microcontroller to the other in the same family or across the families. There will be variation, but this is like the necessary building blocks of the AVR microcontroller. So you have CPU, oscillator, RAM and ROM, interrupt unit ports, and other peripherals. So this is the microcontroller which we are using in our course here. Uh, just a reference again here that we have like numbered the pins in. So if you look at the figure, so you have two different types of numbering. One, which actually numbers the pins on your microcontroller chip from 1 to 28, and from 1 to 28, and then other than that we also have two different colored numberings from like 0 to 13 in red and from 0 to 5 in blue. So the Arduino digital, so this is actually shows you that okay, how the pins of the microcontroller are mapped to the pins on the Arduino board. So for example, pin 5 of the Arduino board is actually pin 28 of your microcontroller chip. And for example, the pin 4 of the Arduino board is actually the pin number 6 on your microcontroller chip. And why we have these two different colors? Because we wanted to just show the digital pins in red. So for example, in our previous lab 3, we were using, let's say, PB0.5. Sorry, no, PB5, like, so which was pin number 13 on our pin number 13 on the microcontroller, right? And blue blue numbered pins on the Arduino, they are analog pins. They are for reading the, for example, if in a project you want to read the values from sensors, so those values are analog values. They are not in digital form. So if we want to do that, then we will interface our sensors with one of these inputs like 0 to 5. If you have any questions at any point, please stop me. So we said that AVR microcontrollers, they are divided into four groups or four families. Classic AVR, Mega, Tiny, and then there are some special purpose AVRs. And these are just some examples of the chip numbers in each of the families. So our at Mega 328, this one, sorry, 328P falls in the Mega family. Uh, and Actually, when you are looking, like for example, in until at this point, all the labs which we have done, what they were doing, we were mostly like writing to a pin. That's all we have done until this point, right? Configuring a pin as in an output mode and then either writing 0 or 1 to it. And by doing that, we were doing different things. For example, blinking an LED, or for example, uh, yeah, that is the most we have done, right? So maybe if let's say you have a project which only needs to blink an LED, then maybe at Mega 328P is an overkill for you, and maybe you can simply use a tiny version of the AVR microcontroller, for example 25 or 80 tiny 13, so which will be sufficient for that kind of project, where you just want to blink an LED. But then they will not be sufficient for other projects where you want to do more sophisticated things. For example, if you want to communicate with your processor, with your computer using USB port, then maybe it will not be possible for these tiny variants, right? uh, how to read these AVR part numbers. So actually these names of the chips, they are not selected randomly, and they carry some information. So the first 80 is basically for the name of the manufacturer, Atmel, and the next is the name of the group. Remember, the AVR chips, they are divided into different groups like classic, Mega, and Tiny. So here it is telling us that this chip falls in the group of Mega. And then the next number, when you start reading it from left to right and you come across a number which is power of 2, then it basically tells you the size of the flash or your program code. So it is telling us here that this particular chip has 128 kilobyte of the program code, program memory. Uh, this one which we are using in our labs. So here everything else is same. That when you read this number from left to right, so 32 is the number which is power of 2. So it basically is telling us that the chip has 32 kilobyte of program memory. This is another example, and here it is telling us that the flash memory is only 4K in size. And this is an example from the classic group, and it has the program memory of only 4K. Okay, so this slide is included just to show that how different AVR microcontrollers they differ from each other. So here, for example, we have two microcontrollers. Both are from the AVR 80 Tiny 25 and 80 Mega 328, but they differ in, for example, number of IO ports or IO pins. So here we have only six IO pins, actually only one port with six pins. And in case of Mega 32, we have four different IO ports, from like port A, port B, port C, and port D. And each one of them is 8 pin wide. So which basically mean that if you are developing project where you need to read values from like read a lot of values from the external world, and you need to write values to the output world, then maybe at Mega 32 is a better fit as compared to 80 Tiny, depending upon what is your requirement. Another difference is, for example, both have this module, which here in case of our Mega 32 is named as SPIR, Serial Peripheral Interface, and here in at Tiny 25 you have Universal Serial Interface. So both of these modules, they are their purpose is to support the serial communication, but Universal Serial Interface, it is a limited version of SPI. So it also implements the SPIX, a Serial Peripheral Interface Communication Protocol, but a subset of that protocol. We don't want to go to the detail of that protocol at this point, but when we will have a lecture on SPI, then we will see that this protocol allows the devices to communicate in two different modes, master mode and the slave mode. So, but the in 80 tiny 25, or this devices can only communicate in master mode, not in the slave mode. So it's like a restricted version of SPI or limited version of SPI. Uh, this at Mega 32, for example, it has Universal Serial Asynchronous Receiver Transmitter or USR, but we don't have this feature available on the Tiny 25. Again, both of them, they support uh, analog to digital conversion or ADC, but their ADCs are different in terms of their capabilities. So on Tiny 25, we have a single channel ADC, but on at Mega 32, it supports 8 channel ADC, which basically means that you can read eight different values from 8 different sensors at the same time. But here you can read values from one analog input at a given time. And then definitely they also differ in their memory sizes and in number of timers. For example, Tiny 25 has 2 kilo ROM and 128 RAM, only 128 byte. And here and Mega 32 has 32 kilo ROM and 2 kilo RAM. And they also differ in terms of in numbers of their timers. So one has only 2 timers, the other one has 3. So it all depends upon like your requirement. So which microcontroller you are going to select, it depends upon your requirement. And also definitely on understanding of your application or understanding of the requirement and understanding of the microcontroller's capabilities. Okay, any questions? No? Okay, so with that, then we are going to a couple of slides which basically only talk about the Arduino Uno board, Arduino boards. So this is the Arduino Uno R3 board which we are using in our labs. But this is not the only board which is developed by Arduino. There are other boards as well. For example, we have Arduino 2019. So it was actually predecessor of Arduino Uno R3 board. So R3 or Uno R3 replaced this board. Uh, and this board actually also uses the AVR microcontroller here. But this microcontroller in the older version of Arduino 2019, 2009 was in the older version, it was 168, and then they replaced it with 328p. Uh, but the main difference between Arduino Uno and this board is basically how they communicate with your computer through USB cable, right? So that the for example here they were using a chip which is named as FTDI. So and here they are not using that chip but a different microcontroller which serves as a bridge between the USB of your laptop and the serial port of the microcontroller. So, what is Arduino? So, Arduino is like a prototyping platform, and it is open source, which basically means you can customize it or you can modify uh, both the hardware and the software as you want for your particular for your purposes. But the this prototyping platform is built around the AVR microcontrollers. Uh, and it actually helps the beginners or designers to first test their product or first test their project before they like go into like let's say mass production. It's very easy to use and it has many choices. I remember when I was in undergrad, we also had a course on like machine programming or assembly language, and we were using the microcontroller 8051. And at that time, it didn't have this board just like now you have Arduino board. So what you had to do is like, for example, now when you program, when you download or burn the program in your Arduino board, what you do is that you simply connect with your USB and you click on your Arduino IDE. You simply click this button, arrow button, and then it burns the code in the program memory of the microcontroller. But when we were using the 8051, so so there was a separate device which was named as burner. So every time you have to program your microcontroller, you will put your microcontroller in that device, then you will latch it there, and then you will connect it with your computer, and then you will burn it. And but after burning, you will again remove your microcontroller and then you put it in your circuit, and then you use it in your circuitry. Otherwise, I mean, it was like it was time consuming in the sense like every time you have to remove your microcontroller from your circuit, put it in the burner, burn it, and then put it back in your in the circuit. So here is another example of board from Arduino, which is named as Arduino Ethernet. Actually, it has the same capabilities as your Arduino Uno R3, but it has an integrated Ethernet controller. It comes with an Ethernet network slot, so you can simply plug in a cable here, and then your microcontroller will be able to communicate over the Ethernet. Uh, this is another example of board from Arduino named as Arduino Mega 2560. Actually, it uses a different microcontroller as compared to Uno R3 board, which uses a Mega 328P. Here, it uses the microcontroller with microcontroller chip 2560. And the main difference from the microcontroller we are studying in the course is like it has more I/O ports, larger RAM and ROM size as compared to at Mega 328P microcontroller. And it is surface mounts. And surface mounts basically mean like if you can see here, there are actually there are two different kind of, not two different, but like for our purpose, there are two different kind of packaging. This is known as dip packaging or dual inline packaging, where you have your chip and then there are legs on both side of the chip, right? And these chips, because of these legs available here, what you can do is that you can put your chip on the chip holder, which is this thing. I don't know if you can see in the figure or not, but I think if you look at your boards or the Arduino kits, you will see that chip is placed on the chip holder. So for example, let's say if your chip malfunctions, or let's say it is burnt out, then what you can do is that simply buy a new chip and put in the placeholder, right? So that's why your Arduino Uno R3 is good for prototyping, right? Or even like even if you are not using Arduino board, but you have this chip, you can simply plug it or put it in your breadboards, right? Because it has legs which can go inside those holes in the breadboard. As compared to this dual inline packaging, uh, this here you have this flat package. In the case of this package, these pins, they don't go inside in the hole on your printed circuit board. They are soldered on the surface, so they don't pierce through the board. That's why then they are called as surface mounted chips. So they are more compact. They take much smaller space as compared to the dip packages, but they are not good for prototyping because, for example, you cannot directly put them on your breadboard when you are building a circuit and you want to first test your project, right? But so that's why if like let's say if you are developing a product and you first want to prototype it, and then you will use the same microcontroller but with this dip packaging. And once you are like sure that okay, everything is fine, and now you want to sell your product on mass scale, then you will use this packaging of the same microcontroller, or flat packaging of the same microcontroller. So all the available capabilities are same, but just packaging is different. Okay. The other thing about Arduino is that it is open source. So software, for example, Arduino IDE, it can be downloaded for free. Hardware design files, they are also available freely and can be downloaded. For example, if you go to the Arduino website, you can download the PCB for your Arduino Uno R3 board, schematics diagrams for the Arduino R3. And if you, for example, you want to build your own PCB, uh, mimicking the original Arduino Uno R3, you can do it, and you don't need to pay anything for that. Uh, and a lot of tutorials are available on how to use these Arduino platform for prototyping, with simple examples. For example, how to blink LEDs, or how to use switches, or how to use pulse width modulation, and so on. So the thing is, like, the Arduino is a very simple platform to use with little knowledge of programming our circuits. Actually, in this course, we are using assembly language, right? But you can also program your microcontroller in C language using Arduino IDE, and it becomes super easy. You don't need to worry about, for example, when you want to blink an LED, you don't need to worry about, okay, uh, what value I need to load a register, and then on what IO port I need to send the value of that register. What is the address of the, let's say, port B data register, and what is the address of port B data direction register, and so on and so forth. You don't need to worry about that because Arduino provides the libraries, and if you use libraries, they take care of all these details for you. But again, we don't want to do that in this course because our target is to learn the assembly language and how to program in assembly language. But if, let's say, if you, once you are comfortable with that, and now you don't want to, like, do the tedious task of programming in assembly, you can simply move to the C language. Uh, and Arduino IDE, it runs with all major platforms or operating systems like Windows, Linux, and Mac. And you can simply power your board using USB, or you can, let's say, for example, when you are prototyping, and once, let's say, you are done with prototyping and now you want to, like, let's say, use in a product, then you can use the external power as well. For example, you can use a battery to power your Arduino board. I'm not going through this slide in detail, definitely, because we are not electrical engineers. But only thing which I want to mention here is that this Arduino schematic diagram is available on the website. So this is for Arduino Uno R3 board, and there are two main chips here. One is the Atmega 328P microcontroller, which is focus of our course, and the other is Atmega 16U2. So this is also a microcontroller from AVR microcontroller, but its job is basically to serve as a converter between USB of your between you have USB of your computer or laptop, and the serial communication port of your AVR microcontroller. And here MU is not the part of the name of the IC or the chip. It is basically a code for packaging, and it indicates that this schematic diagram is using the dip packaging of the this microcontroller at Mega 16U2. So actually, this is your microcontroller, which is used as a converter from USB to serial communication, and it is placed on your Arduino Uno board. Okay. Uh, yeah. And because of this chip, it becomes possible for your Arduino board to simply communicate with your computer in a plug and play mode. So you don't need to do anything. You just plug in, and then it is able to communicate with your computer. So this is like schematic of the simply sub part of that schematic which I showed you earlier, and it shows you how basically your AVR microcontroller is uh, connected on the PCB, a printed circuit board with different components. For example, it shows you here that you need to use a diode here, or for example, you need to put a capacitor here, or so on and so forth. Or for example, you need to convert to connect it with the port here. Uh, and ground and so on and so forth. So this is basically you can use it when you like if you want to say, okay, I don't want to buy the Arduino Uno R3 board from Arduino and I don't want to pay them like let's say $50 or $40 and I want to build my own PCB and it will be cheaper. So then you can use this schematic diagram. Uh, I'm not going through these slides because this is trivial. By this time you are already familiar with the analog and digital I/O pins on the Arduino Uno board. Uh, This is again like kind of redundant, basically saying that our microcontroller, it has flash memory of 16K and each location is 16 bits. So in total there are 16K locations and each location is 16 bit wide. DRAM is DRAM has 2K locations and each location is 8 bit wide. And then EPROM is 1K cross 8 bits. Okay, so just let's have a look quickly at some components at the you must be asking why we are having these slides at this time. We should have seen them earlier in the first lecture. I totally agree with you if you are thinking along those lines. So this is like your power jack on the board. So if you don't want to connect, you don't want to draw the power from the USB cable, you can connect the external power supply. This is the USB interface for like which you need when you are burning the code on the microcontroller. This is your Atmega 16U2 chip, which, as I said earlier, serves as a bridge between between your USB cable, USB port of your computer and your microcontroller, because microcontroller doesn't support the USB protocol. It supports the UART protocol. So these protocol USB and UART, they are not compatible with each other. So that's why we need a translator or converter, and this chip works as a converter for that purpose. And other than that, on this chip, we have two other components. One is known as a resonator. So it is actually the job of resonator is to generate the clock signal. And this one creates the clock signal at a frequency of 16 megahertz and serves as the clock source for your microcontroller. But we also have another clock source on the board, which is a crystal. It is not a resonator. They are actually both of them serve the similar job of creating the clock signal, but the difference is like they are made up of different material. So resonator is made of ceramic material, but the crystal is a quartz, and actually it also has the same frequency of 16 megahertz, but it serves as a clock source for this particular chip at Mega 16U2. And it is more accurate as compared to the resonator. So it provides more precise timing, but then it is more expensive. So that's why they use this cheaper one for the to reduce the size, to reduce the cost of the board. They use the cheaper one for the microcontroller. Uh, Again, this is our famous microcontroller here, and that's it. Okay, someone sent me a test. Why are there two clock sources? Okay, I think I answered your question. Did I or not? Not. Why? Because the thing is like, let me go back. Okay. Okay, so the thing is like this one, the crystal, it provides more accuracy, and which we need when we are communicating with our USB port on the computer. But we can live or we can tolerate lower accuracy when it comes to the microcontroller. So that's why we go for the cheaper option to reduce the cost. Yeah, that's correct. One for the board and one not one for the board, one for actually that one is for the microcontroller, resonator is for the microcontroller, but the other one is for this chip, this small chip here, which as I said acts as a bridge between your USB port and the microcontroller. So this small chips also need a clock source, and that clock source is this crystal. Okay. Uh, any questions at this point related to lectures? No? Okay, so if there are no questions related to lecture, then we are done for the lecture part today. I'm stopping the recording, but if you have questions regarding to labs, as one of your friend he sent me a message, so please stay in the meeting and I will take care of that. Okay, I'm stopping recording.